Hey, good morning. Good morning. All right, let's get the lecture started, okay? So, hey guys, let's get the lecture started. Okay, so in today's lecture, we are going to start on a new type of data structure. So up until this point, here's what we've learned already. We've learned about pointers and how they're used to build classes. You then use classes to be able to do private and public members and methods. You learned about inheritance and polymorphism. You've learned about dynamic arrays and how we can allocate memory to be able to perform the task and abstract that complexity away from the user. So you learned how that benefited you when you took fundamentals of computing and used standard vector. Likewise, you then also learned about linked lists. So we learned about singly linked lists, and we've learned about pointers between them. You've learned about several sorting algorithms. You've learned about recursion, and then you applied inheritance and polymorphism to be able to build a double hash using a linear probe. And this week, what you're working on the creativity challenge is building a sorted doubly linked list and then using class aggregation and inheritance and polymorphism to build a priority queue. So up to that point in the study of computer science, we were just worried about making sure that we could do things efficiently. But now the space race comes along, we get the 1950s and 1960s, and efficiency is no longer good enough. We also have to worry about the weight of the computer. We have to worry about limited amounts of memory. And the reason why is because we can only put so much stuff onto a spaceship, and when we're trying to send things to space, we need to be able to form things correctly, and we have to be able to save as much memory as possible because we can't just throw a bunch of memory up there. And this is the 1960s, and memory is not exactly as light as a laptop like we have today. And in fact, I think whenever you take any photo on one of these modern phones, I forget the exact number they said when I was at I believe it's the entire computing power of the Apollo 11 mission. You get 6 of those every time you take a photograph. So we had to be very efficient. So we want to be able to store as much information as possible. Now, one of the drawbacks of the linked list is that you have to start at one node and traverse all the way through. So we have this trade-off between standard vector, which allocates twice as much memory as we need in the worst case, and we have linked list, in which we still have to have a worst case big O of n access time. So now we need to investigate a data structure that finds a good compromise between those two types of data structures. And to drive this point home, that NASA, when they developed their own embedded C++ programming language to use on the Mars rover, one of the very first things that they did was get rid of standard vector. Too much memory, too inefficient. You need to get rid of it. Now, they went this whole thing, and if you would like to go on, and they have an hour-long presentation, they actually developed their own memory allocator. It's actually really neat stuff. But they had to be very efficient with memory on the Mars rover. Also, they got rid of IOStream, which is not exactly what you need to print to the screen. No one's there to read it. There's no reason for us to have that there. So we're trying to reduce information that we need. So we need a new data structure that stores precisely the amount of information that we need and does not have this worst case big O of n search time. So we have to find this trade-off between a linked list and array, and I made the note, less memory, but longer search time than a hash table. And how do we do this? This idea of a binary search tree. So this is why I've called today's lecture Divide and Conquer. Because if we are able to do a sort and then start at a specific location, I could potentially keep cutting the possible location of the nodes in half every single time. That's why we had big O of n log n, big O of log of n, when we were doing, I'm trying to think of a good example. So remember when we did that problem, we had the longest increasing subsequence, right? And basically, the way you figure it out is that if we had 12, 3, 7, 4, 5, 6, and 9, right? So what we would do is you would start and you would say 12, and then you would say, well, 3 is less than 12, so we're going to put 3 here. We have 7, 4, 5, 6, and 9. So this particular approach that you were taking to replace those values was known as a instance sort. And so the question became, well, what happens if I'm trying to figure out where to put everything? And so we would, instead of having to iterate all the way through, we chose the middle, right? And then we would figure out the location based off of dividing and conquering. And we did the same thing with merge sort, right? So with merge sort, we would divide in half and then try to figure out when we needed to perform a swap. And so quick sort was good as that would keep sorting, and then it's like, okay, now here's an opportune time to cut in half. And now it would actually, that found a good trade-off for that big O of n log n search, which allowed us to be able to perform that search without having to incur the big memory trade-offs with a hash table. So the binary search tree does the same thing. So it was invented in 1960, so this is driven again by the need for fast but efficient memory. And the name of the paper is actually indicative of what it is that they're trying to do. Techniques for recording of and reference to data in a computer. So how can we record information and read to it efficiently? So now we're going to define a tree. So a tree does this by having a linked data structure. So we're going to have the kind of the ideas from a linked list where each node consists of a data element and one or more child nodes, which we will call leaves. So in a linked list, both single and double, we had one child node. That was just next. But we can have more than one, and we're going to go over several different types of trees here over the next week, where we're going to see different trade-offs between what we're going to call the number of outgoing leaves or balancing mechanisms. So let's go through, and I want to do a binary search tree, and first by going through this specific example. So how can I take this set of inputs and come up with a good way to figure this out using divide and conquer? So the way a binary search tree is going to work is we're going to divide for binary. We're going to have a pointer called left and then a pointer called right. And what's going to happen is we are going to compare the value we're going to insert to the current node. If it's less than, we're going to go to the place where we have a pointer and then continue to trace that way. If it's greater than, we're going to go right. And in this particular data structure, we're not going to contain duplicates. So if it's the same, we terminate the call. So this is, we're going to use a lot of recursion in binary search tree operations. So let's go through and start inserting these values. So 30, what's going to happen is 30 is going to be what we're going to call the root node. We're going to have a root pointer that is pointing to the address of this particular node structure. And it's going to have two pointers coming out of it, left and right, that are going to point to null. So currently its children are both null. So the next thing we want to do is we want to insert 20. So we're going to say 30 and 20. 20 is less than 30, so therefore we want to go to the left. So we would go this way, and then we'd see that we have a null location, which means that we have found the appropriate place to put 20. Like so. So what we would do is we would create a node, have that pointer point to that new node, and that would be its new location. So now let's do the same thing with 25. 25 is less than 30, right? But it's greater than 20. So we're going to go this way and then that way. So 25 will show up here as the right child of 25. So where do you think 40 is going to go? Where's 40 going to end up? To the right of what? It's right of 30, very good. And forgive me for saying to the right of what. It's important to specify what it is and why. So I'm trying to build a good habit. So now 50, where's 50 gonna be? Right of 40, very good. And the way we knew that is because we went to the right of 30 and then to the right of 40. 35, where's 35 gonna go? Yes, to the left of 40. The way we did this is because we go right to 30, oh, sorry, like so. And then 10, where's 10 gonna go? Let me check the chat, see if anybody's responded. Where is 10 gonna go? Left of 20, very good. So now, if I want to say, is 25 in this binary search tree, instead of having to search through all of them, I can just say, well, 25 is less than 30, 25 is greater than 20, and I find it, right? If I want to say is 27 in the binary search tree, I would just do the same thing, but then 27 would be greater than 25. I would hit a null pointer, and once I hit a null pointer in my search, this means that the value is not in the tree. And so you can see we only had to do 3 operations instead of 7. And that would be the case if we did this also with 34, right? So this is where the divide and conquer and log of n really starts to become beneficial. It's a trade-off. We only have the number of nodes that we need in memory, but now we have log of n search. And if we have, let me bring up the Google here. So if I have 65536, right? If I say, give me log of that, that's now 16. So if I have a well-balanced tree, I could potentially cut down having to search for 65,536 elements down to 16 choices. So that is the benefit of log of n. That's the reason why we kind of drilled this idea of search and sorting earlier in the semester with recursion, because this approach gives you a significant improvement. Okay, so the first thing I want to do is I'm going to build up a binary search tree from scratch. And at different stages, I'm going to show you code, but I'm also going to show you common mistakes and how we can use the things that we've learned so far this semester to be able to identify why. So in this first piece of code, binary search tree node 1, I've included C standard lib, and the reason why is because we are going to have a lot of null pointers. We are going to, when we create a node, the first thing we're going to do is to say children aren't pointing anywhere. And then later on, we're going to perform operations that will allow us to be able to do this. So it's a templated struct BST node 1. And the 3 struct members are the data element itself. So eventually, since this of course is data structures, we need to be able to differentiate between the binary search tree node's location and its data. And then we have 2 private members that are pointers, left and right. In here, I have a default constructor where we don't have any data. And basically, it just calls the default constructor for that data's type. And then if I have an overloaded constructor, we can put that in there as a binary search tree node with a specific element. So this default constructor and overloaded constructor are very much like how we would do this when we were doing a linked list. We wanted to be able to know that we could create a pointer. And so in a linked list, we could do that for deletion. And also we could create a pointer with the data, so we could actually create a location with some data to point at, so we can start building our tree. And now in BST, a test BST node 1, what I have done is I've created 3 nodes. And they're character nodes, so I have M, B, and R. And now I have, let's set the left and right pointers using addresses. So I have node 1, which contains the character M. And here, And now this is going to help you see why it is that I was drilling this idea of pointers home really early in the semester. Node 1.left is the member of the binary search tree node that is a BST node pointer. That value is equal to the address of node 2. So I've created 3 nodes, right? B and R. And so when I choose left, I just have it pointing there. And likewise, node 1 right is pointing to the address of R. Now the other thing I want to point out is that all of these are pointing to null pointers. Does everybody see that? So every time we create a node, we have to bear in mind where the null pointers are. So I'm going to print out the data for node 1, and then what I'm going to do is I'm going to access node 1's left pointer, dereference it, and then data. So quick question, everybody understands what this minus sign and greater than means, right? Okay, good. Maybe it's because I taught it today in Intro to Computing, I just want to make sure. So then node 1 right data, so what we're going to print out is we're going to print out M, then we're going to print out the data of the node pointed to the left, which is B, and then we're going to print out the node's data that's pointed to the right, which is R. So if I run test BST node 1, and we see that that's exactly what happens. We print out M, B, and then R. Okay, so now we can start creating pointers directly instead of having to do this individually. So what we're going to do here is we're going to create one BST node character called M. And what we're going to do inside is we're going to say node 1 left is equal, using the new keyword BST node, and then we have to template it to a character, and then we're going to use that overloaded constructor that I showed you, and we're going to create the node using that data. So when we create that node using that data, in this particular line of code, we've created the node and we've automatically updated the left pointer of node 1. Does everybody see that? And then we do the same thing with node 1.right. And then I'm going to do the exact same thing that I had in the previous line, but what do you think is going to happen here? So what this piece of code does, and I'm going to bring up it's an article I wrote. Let me minimize this. So we have M, B, R. And what I would like you all to tell me that you think this does, it's node 1 left, then left, then data. Let me open this up to see if they have any questions in the comments in the chat. Okay, so left of 20, so yep, null data is not valid, so FangCon is correct. So what's going to happen when I run this, when I actually run the program? I'll give you a hint, there's a, yes. Very good, you get a seg fault. You notice that it says it right above it in the comment. So let's actually run it and see that what happens. So make test BST node 2. Make sure I should spell test correctly. And we see that we print everything out and then we get a segmentation fault. So the reason why I want to show you this is that when students are working on tree problems, you'll run into segmentation faults all the time. But now because you understand what's going on in the memory, you have a strong understanding of what's going on with pointers and how we do this, this is actually a sign that you're making good progress. If you're running into seg faults, that means, okay, well, I just have to make sure that I allocate everything properly. So on BST node 2.h, what I have done here, yep, very good. Let's see, hide that. In BST node 2, I have now created a destructor, and then I have a copy constructor and an assignment operator. So now we're meeting the rule of 3. So now I've created this to kind of build up that BST node. And then what else I did here is that in order to use that new keyword and make it compile, we have to meet rule of 3 compliance. Okay, so now let's start, now that we've built a node, let's actually start building a binary search tree itself. So what we're going to do is we are going to create a default constructor, and inside of this class, what I'm going to show you when I go to the code is this idea of a root pointer. So previously, up to this point, what I have taught you is that we have a this pointer in a class. And in C++, because of the way in which we try to protect with object-oriented programming, you cannot move where that pointer is at all. And so if I wanted to keep track of the head or tail node, if we updated it in a linked list, okay, I just realized that my question I was answering answered it. So if I had the front or back node in the linked list, I had to maintain a separate head and tail pointer, right? And that's something that would have to be done in C++. In a binary search tree, we are going to have the base pointer called root point to the initial node. And so if the root is null, that means we do not have anything in the tree. And then, just like before with the singly linked list and doubly linked list, what we did is we called delete root. And then we take advantage of recursion. So now what I want to address, and to solve this particular question, we're going to go over 3 very important concepts that you will see several times in job interviews. So the question is, if I want to make a binary search tree compliant, I want to make it meet the rule of 3, I have to create a destructor, I have to create a copy constructor, and I have to create an assignment operator. So how do we copy data and delete data efficiently? So we have an issue. We have to figure out how it is that we're going to do so. So let me run testbst1.cpp, and we're going to see that I'm going to get a compiler error, and I'm going to show you the code. And the parse compiler error says, class BST has pointer data members, but does not override BST character const BST character with a call by reference. So basically what this is saying is that I have not created a copy constructor. Likewise, I have not created an assignment operator. But here's the thing. If I had a linked list and I wanted to create these, basically I would just go through each one. If I had 1, 7, 3, 5, and 2, I'd create a head node, and then I would go to this location, and then I keep moving. And this is pretty simple, right? We just keep going. So if I have a tree, 10, 6, 13, 7, 4, 11, and 15, when I'm copying the binary search tree, I must also preserve the exact ordering, meaning it has to come out to be the exact same tree. Meaning this is an invalid copy. If I made 6 the root, and then 10 is the right, and then 7 would be here, we'd make 13, 11, 15, and 4. The thing on the right is a valid binary search tree. However, if we're copying, it's invalid because we need the exact ordering to match. So first, we are going to figure out how to insert an element into a tree. And then when we start to see how we insert it, we'll also be able to see how to copy it. And then there's a very specific technique for how to copy. So first, when I say cur pointer is equal to null, if I'm initially passing an empty tree, root will be null. And I say cur pointer is equal to new BST node and value. So I'm passing the specific pointer and value. And so root is going to point to 10. And then I just print it out. So now let's say I have another one. I'm inserting 8, I believe the animation will do. So what will happen is it will first say, well, root is not null. And I say value is less than cur data. Then I recursively call insert passing the left pointer. So the left pointer here is null. So then you'll see that we get cur pointer is null there. There we go. All right, so now we get to null, and now we're inserting 25. Bless you. Now we do the same thing, we get to 8, it's going to be less than. So now we've got to the null pointer, we create it, and then we're done. So in the insert method, I've made a deliberate mistake in bst2bad.h. And I'm not going to tell you what it is yet, but let's take a look at this piece of code and figure this out. The first thing I should do is I'm going to bring up bst node bad2. Oh yeah, it's because it's in include. So if I go down here and I go to insert, and I'm actually highlighting where the error is. So when I'm passing all these pointers, what's going to happen when I do this and I pass the result? What do you think will happen with this specific line of code? Any ideas? Yes. Yes, so this is the crucial point. When I have the pointer is in a register, right? So what I'm going to do is I'm going to make a copy, and then when I update that pointer, it will be copied. And so even if I create a new pointer, and then I print that value out, in the local scope, it's going to print and it's going to look right. And so this is something that has frustrated students for as long as binary search trees have existed. I'm using a print statement, and I'm printing everything out. The data is there, but then when I try to print it out at the end, the data is not there. So let me actually run bst2bad, and I'll give you an example of what I mean. A minute. Oh yeah, so test bst2bad, my apologies. Oh, all right, one more time with feeling, I'll get it right this time. All right, so what I have done is I've inserted several nodes, and so here I say in test tst2bad, I've created M, B, and D. I've inserted these elements, and then I've inserted A and Z. And so in my print statement, it actually prints all of them out, right? What happens is when I actually print the tree, and first let me show you, I have an overloaded operator down at the bottom where I print them all out, and I'll go over what I mean by in order in a moment. But if I do, this code is written properly. So it's not actually printing anything out in the tree. It looks through everything else and says there's no tree. It doesn't exist. And so the reason why is because in order to not make a copy and point to that same location, we actually have to call the pointer by reference. So in order to do this, we have to keep track of everything, and we're going to do a preorder traversal. Actually, hold on, let me show you the correct version, BST2 node. So what I'm going to do is I'm going to show you the correct version, if I actually have it open. BST3, there we go. So here in the new insert, look what I've done, star ampersand. I have a pointer to a BST node, and I want to call it by reference, so that way any change that I do will be preserved when we go out of the recursive scope. Does that make sense to everybody? So now here's the other thing about how it is that we're able to preserve and make an exact copy of the binary search tree. And we call this a preorder traversal. Very common interview question. What is the preorder traversal of a specific tree? So I have to preserve the exact order. So in order to do this, what I'm going to do is I am going to construct the nodes in the exact same location. So I'm going to start here, and I would initially create 15. Because 15 is the root node, I want to create the root node. And then I'm going to go left. And then I'm going to create another copy. So the way this is going to work is, I start at 15, and then I'm going to go left, and I'm going to create a copy of 10. And then I'm going to go left again, recursively, and create a copy of 6. And then I stop when both of my children are null. So then I go up to 10 again, and then I investigate the right nodes. So in this case, I now create 12. 12 children are both null. So now I go up to 10. I've investigated both left and right, so that recursive call is done. Then I go up to 15. Now I investigate right. So now I'm at 25. I go left again. 18. Now I'm done. I go up to 25, and then I go to 30. So if I gave you this tree and I said, give me the pre-order traversal of the tree, you will start, you'll go left, and then you'll go right. So it would be 15, 10, 6, you go up, then it's 12, then it's 25, then it's 18, and then it's 30. Right? If you put it in that specific order when you're doing the insertions, you will get the identical tree. Does everybody see that? So actually, let me erase this and just prove it. I'm going to bring up a blank page here. And now I'm going to create a tree with this preorder traversal that we've just done. So the first thing I would do is I would insert 15, and then 10 would go left, 6 would go left, 12 would go here. Then we insert 25, 25 goes there, 18 goes left, and then 30 goes right. Does that make sense? So if you do this specific way, and when I show you the copy constructor that I've done, you'll see that it goes this, left, and then right. So let me scroll down here. And so with the copy constructor, the first thing I do is say, well, if the root's null, just return. Don't do anything. We're not going to cause any trouble. And then I'm going to say the root is equal to copy root data. And then I have this private method copy tree. And in copy tree, I pass both the copy roots pointer and the root pointer of the current tree. And so in copy tree, which is going to be up here, here we are, here's copy tree. I pass the origin by value. And I want to drive this home. It seems counterintuitive because every time you've seen a star, that's passed by reference, right? But in this point, because we're actually passing a node pointer object itself, we're passing the pointer, not the actual node, we're passing the pointer by value. And since I don't want the origin node to change at all, that's good. We've added a level of security. Any changes that were unintentionally made aren't going to be remain there when we're done. For the destination, I have by value, but I call by reference for the destination node. So any change I make to that node will be preserved after we leave the recursive call. So the first thing I do is I say destination node is equal, where we're creating a new node, and I get the origin node's data. So everybody see that? So that's the middle. And then I say, if origin left is not null, I say copy tree, and I say origin node left, and then destination node left. And then I do the same thing with right. So we're going left all the way, and then right all the way. Does that make sense? Likewise, I have a function here, right after it, print in order. So I call an O stream by reference, and then I pass the current node by value, because I don't want anything to change. So if the current node is null, I just return. Otherwise, I print in order. Oh, so that's print in order, excuse me. Here's preorder. So preorder prints the value, then goes left, and then goes right. Does that make sense to everybody? All right, so that is known as a preorder traversal. And if we're doing the copy tree, we're going to go through the whole thing. It's left, I copy left. Then here it's right. I do the right recursive call, it's null. I go up, 25. And then we're done. All right, so again, now we know why this code has a deliberate mistake, because we see that destined node that we want to change is passed by value, even though it has a pointer. So we saw the correct solution that we're going to call by reference. The assignment operator is the same thing. We do assign.root. We do the same thing that we've done all the way through the semester. We said if this does not equal the address of assign, that means we're not trying to copy itself. And then assign.root equals null. We return star this. Otherwise, we'll say the root is equal to the data of this binary search tree. And then we do copy tree again. So now we just take advantage of that private method, excuse me, and just do the work for us. And then here we have BST, we're returning the address, which is why we're dereferencing this. We learned all the way back in the beginning of the semester, week 1, that the this pointer contains the address that we're pointing to. So when we dereference this, we are getting the address of BST. Right, does that make sense? All right, let me check the chat real quick. We don't have anything in the chat. All right, so next thing, common interview question. Give me the in-order traversal. So in in-order traversal, we actually want to print the values of the binary search tree in order. So the simple thing is, we would look at this and go, okay, well, I would know that this tree 6, 10, 12, 15, 25, and 30, right? So intuitively, I can figure that out. Remember, the computer is doing the same thing that we're doing in our brain. So here's how we're going to figure this out. We are going to look here, and we know that the smallest element should be to the left. So we're going to keep going left until we hit a node that has 2 null pointers, right? So 6 would be the first element in the preorder traversal. Then we go up, we get the middle element, so it's going to be 10, and then 12 is going to be the right element because it's bigger. So 6, 10, and 12. Then we go 15. Then we go right, so 25. Left is null, so then we go right, and then it's going to be 30. So here we would call the method print in order. That's the one that I inadvertently showed you. So at print in order, what that does is it says print left, so it's calling recursively first, then it says print the middle, then we recursively go right. And so if we do that, and again, what should happen here, this is, we've now proven why this code won't work. What should happen is it should add A and Z, like so, because we have two different trees, but because we were passing by value instead of reference, nothing printed out. So then we update our call by reference. We're updating insert, so we have to change that with an ampersand. Otherwise, the code is exactly the same, and now it will work. So if I run make test bst2, it's going to be the same thing. It's just going to call the correct tree, and we're going to see that it prints everything out: BDM, ABDM, and BDMZ. So we create in testbst2.cpp. What we have done here is we've M, B, and D, right? And then I use the copy constructor to make tree 2. I use the assignment operator to make tree 3. And this is a really good test to make sure that your copy constructors and assignment operators are doing what you want them to do. Because here I've inserted A into tree 2. So A should be, we should have M, B, A, M, B, yeah, like so. Right, so it should be A, B, D, M. And then if we insert Z into tree 3, it should look like this. And that's exactly what happened. We do not unintentionally have a copy of A in tree 3, and we do not unintentionally have a copy of Z in tree 2. We have all of the elements B, D, and M from the original tree. Does everybody see that? So we're starting to build a binary search tree. So now I've already shown you the pre-order print. So we have the output, then we go left, and then we go right, and that shows us the exact order that we would need to insert in order to create the exact same tree. And now I have my operator where I'm going to print out in the operator, when I print the binary search tree, it's going to print the pre-order and in-order traversal of the tree. And so now when I run make test bst3, it's the exact same code, but now we see that in order, BDM, so I know the logical order of the tree, but I also know that if I want to create the exact same tree, I need to go B, M, B, D, and Z. For in order, A, B, D, and M in tree 2, but to create the same tree, I have to go M, B, A, and D. And in order for tree 3, B, D, M, and Z, but to get the exact tree, if you insert M, B, D, and Z, you will get the exact same tree. Right, so now here's another important one, post-order traversal. Tell me what the post-order traversal of the tree is. So post-order is the opposite of pre-order. Pre-order, we went left, right, and then middle. Here we're going to go right, left, and then middle. So why is this important to be able to do so? So if I go right, if I go 30, so the post-order traversal would be right, left, and then middle. So there's nothing over here. So this would be 30, 25, 12, 6, 10, and then 15. So the question is, why is this important to understand? One really good use for this is this tells us the order that we need to be able to delete the tree in order to be able to successfully delete all of the elements. So for example, I have this pointer here, and I just delete 25. What is the big problem if I just do that? What happens here? Yes? Can't access 30 anymore. So if I'm going through and I delete all the rest of these, the node for 30 is still in the data heap. So that is known as a memory leak. We can no longer access that memory, and while we're running our program, we can no longer guarantee that we can access that location to be able to perform tasks. So if we want to delete them in a specific order, we want to delete from bottom up. So I start at 30, nothing's over there, so we're good. Then I can delete 25, but I can't delete 15 because then I can't access those other elements. So now I'm going to go left, but then I start going right again. So here I do 12, 6, and now that both of those are deleted, I can delete 10 safely, and then finally I delete 15. So the post-order traversal is right, left, and then middle. And that is the exact order in the animation. Now delete node, I call delete node root. In this method, void delete node, we're now going to use that same kind of recursive idea. Remember in linked lists where we call delete root, and then each of those nodes had its own private member and it stopped deleting when we hit null? We're going to use that same to be able to simply delete a node from a binary search tree. We're going to delete the binary search tree by calling delete node root. So here I call by reference again, because we want to maintain the integrity of the changes. If it's equal to null, we return. Otherwise, we delete right, then we delete left, and then we delete the current pointer. And that allows us to completely free the entire tree. To print and post order, it's the same thing, except I call print post order right, print post order left, and then print the middle element. And now I've updated in bst4.h, I've just added the function, the method print post order, and I'm calling output and then tree.root. So now this overloaded operator will print in order, pre-order, and post-order traversals. And so now make bst4, run that just to, that code is identical, except now I'm running it off of the new binary search tree. And now we've printed pre-order, in order, and post-order. And we see that our post-order, should be D, B, and M, which is exactly what happens. Here we should have D, B, A, and M. And then here we have Z, D, B, and M, and that's exactly what happens in post order. So for the last thing, so this is what we'll cover over the last minute of lecture. Level order traversals tells me which nodes are ordering if I were to go down the tree by level. So let me ask you, based on something we've done a lot over the last week or so, and in fact, we actually have done it over the last couple of weeks, what would be an approach, and I'll use graphs, go all the way back to 4, 25, we had 10, 30, and 7, right? So we had just some random graph, right? If I wanted to get the level order, what search algorithm would give me this? If my output I wanted to be 4, 20, then 5, then I could do 7, 30, and 10. Yes, in the back. Breadth first search. And what is the data structure that we use to be able to accomplish a breadth first search? It's a word and a letter together, both of you. Both of you are right, it is a queue. So we can do this in the same way. Pattern looks familiar, breadth first search, and we call a tree a directed acyclic graph. Nothing goes back, it only goes in one direction, and we use a queue, so you're all absolutely right. And then I just create a set of void pointers to be able to keep track of the address of each node, and this allows me to do this. So what I'm going to do is I'm going to start Friday's lecture by going over this code segment, and then I will go into VST deletion, and then we'll study a data structure called an AVL tree. Let me quickly check. We had one question in the chat. Topological sort would do that. Yes. That is exactly what happens. All right, so y'all have a wonderful day, and I'll see you all on Friday.